Hello, my name is Graham Sexton and I'm going to be trying to take you through how to build a very basic throughput model for your assignment on this series of slides. So let's just take a look at what the context is, and in your assignment you're looking at estimating the throughput across a wireless link, and here on the left hand side of the diagram we've got a wireless interface card, on the right hand side we've got our access point, and there's a wireless communication link between the two, and what we're interested in is estimating the throughput across that wireless link. Now, in terms of calculating that throughput, what we're really thinking about is looking at the payload that's transmitted on this side, on the wireless side, and looking at how much time it takes to transmit that payload across the wireless link. So we end up with a very simple formula where the throughput is equal to the payload divided by the time it takes to transmit that payload across the link. Of course, there are some complications in working out exactly what the time is in particular, and we'll look at that very, very briefly. The payload is much simpler. So if we're thinking of generating the wireless traffic using something like iPerf, using a UDP connection, then the payload is the size of the UDP payload that we're creating at that particular time. But the time is more complicated than that. So the time will be taken up by, first of all, the time it takes to transmit the payload itself. So we'll just represent that by this little rectangle, payload. But it's not just the payload that gets transmitted across the link. As we pass the payload down our network stack, we add various bits and pieces to it. So at the next layer down, in fact at the UDP layer, we add our UDP header to that payload. The data continues to be transmitted down the network stack before it's transmitted, and we add to that our IP header, and we're still not finished. And next layer down, we add to that a MAC header, or network layer header, a data link layer header, and then the next layer down, let's get all those bits, we've got a physical layer. I'm kind of reluctant to call it a header, but at the physical layer there are bits and pieces of data that we end up adding to it. So the whole transmission consists of this piece of data here, and that obviously will take longer to transmit than just purely the payload alone. So we're not quite finished there either, because in this particular instance we're talking about a Wi-Fi link between the 2 points. So Wi-Fi has a protocol to transmit the data, and it involves some detail which is in the lecture notes and can be found elsewhere, but involves some time delays before transmission. The time it takes to transmit the actual data lump, and the time it takes to create the acknowledgement of that packet. So that's some additional time. So I'm going to add that here, and I'm just going to mark that as Wi-Fi overhead. So the overall time, in fact, looks more like this. So that period here is T, which is this time here. Now this is a fairly simple model. There are other models around there, that you'll find in papers, but nonetheless I think this embodies most of the ideas that we've got in our papers. So now I want to take a look at how we might build that model using an Excel spreadsheet. So let's take a look at this spreadsheet that I've prepared earlier, and this spreadsheet is only representative of one possible spreadsheet that you might produce to do a modeling process. I'm not suggesting that this is the spreadsheet that you should all be using at all. Indeed, the quantities that I'm using here might not be the correct quantities. So if you see something in here that you don't agree with, that's not a problem. Just make sure that you get the right quantity that you want to use. So let's just take a look at this spreadsheet anyway. So beginning at the left hand side, at the left top in cell A2, we have a title payload, and that's probably the starting point for our spreadsheet. And I've got a payload that's varying. I'll just mark that payload column. That's the payload that's varying between 100 and 3000 bytes. That is not necessarily the range that you want to use. It's just purely the range that I've actually put in this particular spreadsheet for convenience. Next to that, I've got the raw bit rate value. The standard I've chosen to model in this particular spreadsheet is the 802.11 spreadsheet. It's not necessarily the one that you'll be using. If you're doing A or G, you should have 54 million in there instead of 11 million. And the first calculation column here is payload T, which is the time it takes to transmit purely the payload itself. And if we just have a look at the first cell in that column, let's get that right. Hang on a second, it's just that the penning is getting in the way. Let's just remove that penning. Right, there we go. We can see that the cell formula in the formula bar. No, it doesn't seem I can draw on that part of the spreadsheet, but the cell formula is A3 divided by B3, which is exactly what you would expect. It's basically the payload divided by the raw bit rate will give us the time it takes to transmit purely the payload itself. Of course, that's not the only time involved, as we saw from the previous slide, but we need to take into account all of the overheads that are highlighted in yellow on this spreadsheet, and the overheads are broken down into two parts: those overheads which are concerned with the network stack and the overheads that are concerned with the 802.11 transmission. So the overheads that are associated with the network stack are UDP, IP, MAC, and physical, and we have that final column which is indicative of the overall time it takes to transmit those overheads. And then we have the diffs period, contention period, sifts period, and the time it takes to transmit the acknowledgement. So let's just take a look at, first of all, at the UDP component. So UDP, you need to have a look to see how big the UDP packet is, I think what you'll find in most cases, it will be 8 bytes big, so you need to translate that into the number of bits to make sure that we're operating in bits alone for this spreadsheet. Take a look at the IP header. Again, you'll find that is normally 20 bytes big, but sometimes it can be bigger. So in your case, you need to make sure that your IP header is in fact 20 bytes and not some other size. It really depends on how you have your system set up, but I'm assuming it's 20 bytes. I haven't put anything in the MAC or the physical layer overheads, and I'm going to ask you to do that exploration and find out what those details are yourself, and just pop those values in there. I think you'll be able to find that out in a relatively short period of time. It's fairly well documented, and you shouldn't really have any problem arriving at those values. Just remember to make sure you pop them in there as bits. And looking at this column with the column header OT, which is I'm calling overheads time. The overheads time is essentially, if I double click on that, we can see that the overheads time is the sum of the UDP, IP, MAC and physical layer divided by the raw bit rate, and that gives us an estimate of the time it takes just to transmit the overheads itself. So we additionally have to take into account the diffs, contention, sifs and acknowledgement periods. I'm going to let you find those out. They're pretty well documented. The only thing that you need to be a little bit careful with is to make sure that you check to make sure that you're reading that data for the right standard, and the acknowledgement sometimes is listed or documented in terms of bit or byte size. You need to be careful about how the acknowledgement is transmitted. It's not normally transmitted 11 megabits per second, but it's normally transmitted at 1 or 2 megabits per second. You need to take a look at your system to find out its transmission rate, and that will require you a little bit of extra research, but it's really not too hard to find if you use a tool like PCAP with Wireshark, and it'll tell you the transmission rate of the acknowledgement. The other thing that I would just warn you of is you just need to take care with the units that you use to represent the diffs, contention and sifs period. It might be listed in milliseconds or microseconds, and if you simply just put in milliseconds or microseconds, you're in trouble, because the units in your spreadsheet in terms of overhead time, at least that I've got, the units are seconds, and you need to make sure that you just stick with the right units, and that's pretty straightforward stuff. Total time. So the total time that it takes to transmit all of this stuff. Let's just take a look at that calculation. So the total time is the time it takes to transmit the payload plus the overheads due to the protocol stack, plus the overheads due to the Wi-Fi as well, and that gives us the column value for the overall overheads. The throughput, the final column, that probably is this most straightforward calculation, which essentially, if we double click on that again, we can see the cells involved. So it is the payload, that's the leftmost column, divided by the total time, and that gives us the actual throughput. So let's just take a look at what that looks like in a graph. So I'm going to select the payload column. It's column A, so I'm just dragging the mouse down, releasing the mouse, pressing Control and keeping the Control button pressed and dragging down and selecting the throughput column. So I have those two columns selected now, and I'm going to click on the recommended chart button there. And here we have our recommended chart. I'm going to accept that as a chart. And looking at that, the general form of this chart is correct. We'd expect this type of curve. The values that are showing on this chart are okay for the simulation model that I built here, but they're not okay for the final model. What I haven't taken into account are the MAC overheads, the physical layer overheads, and all the Wi-Fi overheads. So the throughput is far too optimistic. We will not achieve that level of throughput. Well, I'm saying far too optimistic. It's a bit optimistic anyway. So we'll actually achieve a lower throughput for at least this particular model. The graph I would just add would not be quite satisfactory for your report as it stands. It doesn't have the axes labeled, the title is poor, it doesn't have units on the axes, etc, etc. So the presentation of the graph is not really quite up to scratch, but nonetheless it illustrates the basic form of the data, and you should be seeing something like this in any case. So I hope this has been helpful in at least giving you a pointer in the right direction for building this throughput model, and you can then of course use this throughput model to compare those results with your practical results. And if you do have any further questions, please don't hesitate to ask me directly in class. Okay, thank you for watching.